Hi guys, welcome to the next chapter. We're going to start rotational motion in this chapter, and we're going to take our beginning rotation all the way up through something called torque, and then we're going to finish rotational in the next chapter. It's a pretty big topic, but we have to start off with, we have to make a connection between what we've done so far, which is linear motion. And remember, translational and linear mean the same thing. So they're synonyms. And to do that, I have an app. So I'm going to share my screen here. And minimize that. So what you can see is I have a wheel and the spokes have colors so that I can pay attention to how many times the wheel turns. Down here I have a ruler, and that's going to show me how far I go with a linear distance. So what we're going to do here is we're going to compare our linear distance. We're going to look at the distance traveled by both in a straight line, and then we're going to look at the distance traveled in a circle. Now, most of you are probably familiar with degrees. And so right now I'm going to assume everybody knows that one circle is 360 degrees. That's not the unit we want, but that's our starting point. So I have set my radius to be 200 millimeters or 2 meters. And I'm going to let this rotate one revolution or 360 degrees. And we'll watch as this, the red spoke goes up. And when it comes back down to this position, I'll stop it. Now, we're going to start off, we're going to imagine we're looking at a point right here at my cursor. Well, then I'm going to ask you what's going to happen if we're here. So keep those two things in mind as we run this simulation. Okay, here we go. I'm going to start. And I'm going to see if then I can stop it when it hits one revolution. Oh, I was close. I'm a little off. So I should have let it go just a little bit further. But you can see that in one revolution at a 2 meter radius, I traveled about, let's see, this is in centimeters. So I would have been at about 1.4 if I hadn't stopped it a little prematurely. So now I'm going to reset it. And I want to change my radius. Before I do that, I want you to imagine that during that revolution, that 360 degrees, I was now a point on this part of the wheel, on this part of the spoke. Did I travel the same distance? Take a second and think about that. Pause the video if you need to. All right, what I'm going to do now is I'm going to have my radius. I'm going to drop down to 100 millimeters. So now the particle here is at that distance we were talking about, and we're going to let that run. I'm going to let that run for 360 degrees or one revolution. Oops, and that one time I went a little too far, but you can see here I'm at about 60, it would have been about 62 or 63 centimeters. So I had about half of the distance. Did my rotational motion change at all? No, it didn't. I went almost 360 degrees both times. So what we see is that I have to compare my two different types of motion. I have rotational motion and I have linear motion. Rotational motion, and I'm going to stop sharing my screen. Let me hit reset. And values for rotational motion are what we call angular values. Angular values. Linear is what we've been working with, where that's meters per second squared, but angular is something new. So what we can see, there's actually a formula that's going to relate the two. My linear distance, my symbol for that is x, but my angular displacement is going to be theta. And the relationship between these two is that my linear distance is equal to the radius times theta. So this ties together my translational and my rotational. And here's the deal. Every point on that spoke had the same rotational, had the same angular displacement, because they all traveled through the same number of degrees going in a circle. But every point on that spoke had a different linear value, and that was dependent on where it sat on the spoke. So all points, I'm going to write this in red because it's important. All points on a rotating object have the same angular values. Have the same angular values. Because translational or linear and angular, and I'm going to switch to saying linear and angular, because they're not the same, we use different symbols. So if I'm going to continue with this, let me do a little linear and angular. I should have done a table probably. Linear and angular. We said displacement is x, and for angular, it's theta. Velocity for linear is v, and for acceleration is a. What they've done for angular values is they've gone into the Greek alphabet. The Greek lowercase letter for a, or the letter for a is alpha, and lowercase, it looks like that. Kind of looks like half a fish. It's open on one side. Now, our last letter is z, but the Greek alphabet doesn't have a letter z. The last letter in the Greek alphabet is omega, which is as close to v as we're going to get. Lowercase omega looks like a lopsided W. So this is angular displacement, this is angular velocity, this is angular acceleration. This is linear displacement, linear velocity, and linear acceleration. And we saw that the displacements were tied together this way. Our angular values for angular velocity and angular acceleration relate the same way. So if I take v, I get that is equal to r times omega, and linear acceleration is equal to r times alpha. So that's how we always convert between the linear and the angular, is you multiply the angular value times the radius. Now let's switch gears a little bit and let's talk about units. So we talked about 1 revolution. That's a unit. We talked about degrees. So we know 1 revolution is 360 degrees. But the unit that we really want to use for rotational motion is radians. How many radians are in a circle? Hopefully you said 2 pi. And in a lot of your math classes, we keep pi in the form of pi, but in physics, it's common to approximate it. So if you take 2 times 3.14, you get 6.28 radians in 1 revolution, or in 360 degrees. So we end up with conversion factors. We say that 1 revolution is 6.28 radians, or we could say that 360 degrees is 6.28 radians. And you always have to make sure that you have put your values into radians, just like we had to do in linear, where we have to know our masses in kilograms and our distances in meters. So let's take a look at a couple of sample problems. What is the linear displacement of a wheel with a 0.1 meter radius after 1.5 revolutions? So we want to solve for linear displacement, which is x. And we're given theta, and we're given radius, but this is in revolutions and not in radians. So I have to convert 1.5 revolutions. And if you remember your dimensional analysis from chemistry, I'm going to multiply that by the conversion factor, where I have 1 revolution is 6.28 radians. And I'm going to get a value of 9.42 radians. So in order to solve for x, I know that x equals r theta. So that's going to be 0.1 times 9.42. And that's going to be 0.942 meters. All right, well, let's go test this and see if this is accurate. I'm going to go back to my sim. And we have a 0.1 meter radius, I believe. Oops. Well, let's just go with what we've got because it'll be scaled, but it'll be the same. And I'm going to go 1.5 revolutions. So I'm going to go around and I'm going to come up a half. So here is 1, and I'm going to go to a half. And I was a little bit, again, I didn't quite nail that at the upright position. If I had, I would have seen that I was the 0.94 meter mark. So yeah, it's good. All right, let's do another one. What is the linear velocity of a wheel with a 0.1 radius if it turns 2 revolutions in 0.97 seconds? Okay, so we said earlier that our translational velocity is going to be equal to the radius times our angular velocity. And if our translational velocity is displacement over time, we know that angular velocity is going to be radians over time. So we have got, we're solving for V, what we're solving for. So I have V equals R times my radians over time. So I have R is 0.1 and my time is 0.97 seconds, but I have 2 revolutions. So if 1 revolution is 6.28, if I multiply that by 2, I'm going to have 12.56 radians. And when I solve, I end up with a linear velocity of 1.29 meters per second. What are our takeaways? Linear and angular. The linear values for any point on a rotating object depend on where it's at, but the angular values are the same for anything in a line on a given radius for a rotating object because they carve out those same number of degrees. And then we can put these into equations where we equate both displacement and velocity and acceleration according to that. So we have linear on this side, we have angular on this side. We use Greek letters for angular, and then we went through these couple of sample problems to kind of help you with your conversions. And the first homework assignment is just converting angular to linear, and then the second one takes you into these equations a little bit. All right, that gets us started for rotational motion. Thanks for watching.